Let's review for Chapter 3's exam. Question 1. Match of the following equation with the description of the parabola that is its graph. We have the equation y equals x plus 9 squared plus 6. Recall the vertex form for a parabola is x minus h squared plus k. The hk is going to tell us the location of the vertex. In our case, we have h, k here. H is negative 9 and k is positive 6. If you look at the equation, we have an x minus h here. Here we have a plus sign, but you can consider it a double negative, and so h is negative 9. Do not make the mistake that h is positive 9. K is this 6 here on the right, and that's why the vertex is negative 9, 6. If you look at the front of our parabola, we have a positive 1 in the front. That means the parabola is going to open upwards. It's going to face up because the number in the front of a parabola is positive 1. And so the only option that has that is this option here. We have the parabola y equals x plus 9 squared plus 6 has a vertex of negative 9, 6, and it's going to open upwards. Question 2. Let's graph the quadratic function f of x equals x squared minus 14x plus 45. I want to also give the vertex, the axis of symmetry, state the domain, and give the range. We also want to determine the largest open interval of the domain over which the function is increasing, and the largest open interval over which the function is decreasing. So there's many parts to this question. Let's start off with part A. In part A, I want to find the vertex. In order to find the vertex of our function x squared minus 14x plus 45, we need to complete the square. And to do that, we need this formula, b divided by 2 squared. In our case, our b is negative 14. So we'll take negative 14 divided by 2 and square it. This is equivalent to 49. Let's rewrite our function. F of x is equal to x squared minus 14x plus 49 plus 45. Now notice we added a 49. You cannot do that and have the same function. So we have to subtract 49 on the same side. So this function is exactly the same as the original function. Now I can complete the square. F of x can be rewritten by factoring this part as x minus 7 squared. This part becomes x minus 7 squared if you were to factor it. And now we can simplify the right side. 45 minus 49. That's equal to negative 4. Now why did we spend all of this effort to rewrite our quadratic function in this form? Well, that allows me to look at the vertex using our vertex form. In our case, we have h, k is the location of the vertex. So the vertex is located at 7, negative 4. This is our solution for part A. The vertex is 7, negative 4. In part B, we want to state the axis of symmetry. If I were to plot this parabola, I would know it faces up because the leading coefficient is a positive number. So we know this parabola faces up, and the location of the vertex is 7, 4. So here's a rough sketch of what it looks like. We have the vertex at 7, 4, and it's going to face up. This is just a rough sketch, but it allows me to see what the graph looks like. Now I know the axis of symmetry is going to run straight to the vertex. It's going to cross the x-intercept here at x equals 7. This is our axis of symmetry, x equals 7. And that answers question B. What is the axis of symmetry? The vertical line, x equals 7, is our axis of symmetry. In part C, we want to determine what is the domain. The domain is how far left the graph goes to how far right the graph goes. The domain is negative infinity to infinity. In part E, we want to figure out the largest open interval for which the function is increasing. The function increases from the vertex here as we go to the right. So it's increasing from x equals 7 to infinity. So the open interval, it specifies we want an open interval for which it's increasing. So it's going to increase from 7, when x is 7, all the way to infinity. It's decreasing from negative infinity all the way to 7. And again, for part E and F, they request that these intervals be open intervals. That's why we do not use square brackets for our solutions in part E and F. Question 3. Let's solve the following inequality by using a graphical method. Let's consider x squared minus 3x minus 10 is less than 0. The first thing I want to do is to find the zeros of this quadratic function. I can set x squared minus 3x minus 10 equal to 0, and this allows me to factor this. This factors as x minus 5 times x plus 2 equal to 0. Here we're using the diamond method with negative 10 on the top and negative 3 on the bottom. The two numbers that work are, of course, negative 5 and positive 2. The solutions to this is x equals 5 or x equals negative 2. This means that 5 and negative 2 are not part of our solution set. Because if you look at the original inequality, we want values that are strictly less than 0. This is equal to 0 here. So these are not part of our solution set because of that inequality, and that's why I need open circles at negative 2 and 5. What about all of the other regions below negative 2, between negative 2 and 5, and above 5? We'll have to pick some test points. So let's pick some test points. I want to test any number that I want that is less than negative 2. Let's test x equals negative 3. And I could plug this back into the original inequality. We have negative 3 squared minus 3 times negative 3 minus 10. Is that less than 0? And we'll have to figure that out. Negative 3 squared is 9. Negative 3 times negative 3 is positive 9 minus 10. That's less than 0. And we have that this is in fact false because 9 plus 9 is 18. 18 minus 10 is 8. 8 is not less than 0. This is false. This is false. So that means the solution set is not to the left of negative 2. It is not part of this region on the left. Now let's check a number between negative 2 and 5. I always use something easy. Let's test x equals 0. We want to plug in x equals 0 again into our original inequality. We'll plug in a 0 for the x. 0 squared minus 3 times 0 minus 10. Is that less than 0? And this is clearly true. We have negative 10 is clearly less than 0. This is true. That means I could shade between negative 2 and 5. This produces a value that is less than 0, and that's what we want. And now we have to test one more number. Let's test a number larger than 5. Let's test x equals 6. Again, we're going to plug it into the x for the original function. You have 6 squared minus 3 times 6 minus 10. Is that less than 0? This is 36 minus 18 minus 10. Is that less than 0? This is 8 is less than 0. That's a false statement. So that means this is not part of our solution set. What is our solution? What is our solution? Our solution is everything between -2 and 5. This is the solution in interval notation. Let's visualize what this means. This means we have a parabola that has zeros at -2 and 5. It faces up because the leading coefficient is positive. And we're asking, when is the graph less than 0? That means when does it dip below the x-axis? Well, that's exactly between -2 and 5. In question 4, let's use synthetic division to perform the division. Before I start synthetic division, I need to make sure this is in descending orders of power. We have a power of 3, power of 2, power of 1, and a power of 0, so we're okay with the numerator. To do synthetic division, make sure we put a -3 here on the outside. We have an x plus 3 here, so I want to make sure I use a -3 here for our divisor. Our coefficients are 1, 5, 9, and 9. We'll drop down the 1, and then we'll multiply. -3 times 1 is -3. Then we'll add 5 minus 3 is 2. We'll multiply again. -3 times 2 is -6. 9 plus -6 is +3. -3 times 3 is -9, and that adds up to 0. This is our remainder. There is a remainder of 0. That means it divides perfectly into x plus 3. Let's write our solution. Recall our solution is going to have 1 power less than the original function. 1 power less would be a power of 2, so this is equivalent to x squared. The leading coefficient here is a 1. The next number is a 2, so it's plus 2x. And the last one's a 3. So this is our solution, x squared plus 2x plus 3 using synthetic division. Question 5. Let's use synthetic division to perform the division again. We have x minus 2 is our divisor, so we'll have a 2 on the outside. And notice in the numerator, all of the powers are in descending orders of power, so we're okay with that. We'll put the leading coefficients. The leading coefficients are -7, +6, -8, and +9. Then we could bring down the -7 first and multiply. 2 times -7 is -14. 6 minus 14 gives us -8. 2 times -8 is -16. And -8 minus 16 is -24. -24 times 2 is -48. If I add 9 minus 48, we have -39. We started off with a power of 3. That means when we use synthetic division, we should have a power of 2. So let's write our solution. -7x squared minus 8x minus 24. But recall this, -39 is our remainder. So we'll have to add our remainder as -39 divided by our divisor, which is x minus 2. And this is our solution for question 5. -7x squared minus 8x minus 24 plus our remainder, -39 over x minus 2. Question 6. Use the remainder theorem and synthetic division to find f of k for the given value of k. Here we have a cubic function, f of x equals -2x cubed minus 12x squared minus 11x minus 5, and k is equal to -5. Let's use synthetic division. We have negative 5 on the outside, and on the inside we'll use our coefficients. Our coefficients are negative 2, negative 12, negative 11, and negative 5. The first step is to bring down that negative 2. Negative 5 times negative 2 is positive 10. Negative 12 plus 10 is negative 2. Negative 5 times negative 2 is a positive 10. And when we add these two up, we have a negative 1. Negative 5 times negative 1 is positive 5. Negative 5 plus 5 gives us a remainder of 0. The remainder is 0. But according to the remainder theorem, f of negative 5 is equal to the remainder, which is 0. So I know f of negative 5 is exactly 0. Question 7. Use synthetic division to decide whether the given number k is a 0 of the given polynomial function. If it is not, give the value of f of k. We are given that k is 1 plus I, so we'll put that on the outside, and on the inside we'll put our coefficients. The coefficients are 1, 5, negative 3, and positive 2. We'll start by bringing down the 1 and multiply. 1 times 1 plus I is 1 plus I. 5 plus 1 plus I is 6 plus I. Now I'll need to multiply 1 plus I times 6 plus I. We'll do the scratch work on the side. 1 plus I times 6 plus I. We'll have to FOIL. 1 times 6 is 6. 1 times I is I. Then we have a 6i. And I times I is I squared. 6 plus I plus 6i is 7i, and we know I squared is equal to negative 1. This simplifies to 5 plus 7i. So we'll write 5 plus 7i here, and then we could add negative 3 plus 5 plus 7i, which gives me 2 plus 7i. Then again, we'll have to multiply. We'll have to multiply 1 plus I times 2 plus 7i. 1 times 2 is 2. 1 times 7i is 7i. I times 2 is 2i. And I times 7 is going to give us 7i squared. We can collect like terms. We have 2 plus 9i. And 7i squared is equivalent to negative 7. 2 minus 7 is negative 5. And then we'll bring down the 9i. So the product of 1 plus I and 2 plus 7i is negative 5 plus 9i. Then we could add 2 plus negative 5 plus 9i, and that's going to give me negative 3 plus 9i. This is our remainder. This is our remainder. That means 1 plus I is not a 0. And therefore f of 1 plus I is equivalent to negative 3 plus 9i from the remainder theorem. 1 plus I is not a 0, and therefore f of 1 plus I is equal to negative 3 plus 9i. Question 8, let's factor f of x into linear factors given that k is a 0 of f of x. F of x is 4x cubed plus 27x squared minus 39x plus 8, and we're given that k equals 1 is a 0 of f of x. When we use synthetic division, our remainder has to be 0 because we're given that k equals 1 is a 0 of f of x. Let's put our coefficients. Our coefficients are 4, 27, negative 39, and positive 8. When we use synthetic division, again, our remainder must be 0 because we're given that this is a 0. We'll drop down the 4. 1 times 4 is 4. 27 plus 4 is 31. 1 plus 31. 1 times 31 is 31. Negative 39 plus 31 is a negative 8. 1 times negative 8 is negative 8, and we do get a remainder of 0. That's what we expect. Now, what does this tell me? Since we're given k equals 1 is a remainder, we can rewrite 4x cubed plus 27x squared minus 39x plus 8 as a factor of x minus 1, because we know k equals 1 is a 0. Therefore, x minus 1 must be a factor. What is the remaining factor? Well, the remaining factor is right here. And since we started off with a power of 3, this has to start off with a power of 2. This is 4x squared plus 31x minus 8. But we can factor this further. This is the AC method. Let's multiply 4 times negative 8. That's going to give us negative 32. And on the bottom is 31. The two numbers that work are positive 32 and negative 1. Now you could go about it in multiple different ways. You could use the AC method by splitting the middle, or you could use the AC method by using the bottoms up method. I'm going to use the bottoms up method here, and that's to divide both of these by 4x, and then we'll reduce to lowest terms. This reduces to 8 over x, and this one is still negative 1 over 4x. We'll bring the bottom up here, and so this factors as x plus 8 and 4x minus 1. Again, you could factor this many different ways. You could use trial and error, you could split the middle, or you could use the bottoms up method here. Whatever you like. So this factors as x minus 1, and we just factored this here on the left as x plus 8 times 4x minus 1. This is our solution. This is the factored form of our original polynomial. Question 9. For the following function, 1 0 is given. Find all the other zeros. We have f of x equals x cubed minus 8x squared plus 21x minus 20. And we're given that 2 minus I is a 0. If 2 minus I is a 0, that also implies that the conjugate 2 plus I is also a 0. This is going to be a difficult problem because we'll have to use synthetic division with a complex number. So let's start with 2 minus I on the outside, and on the inside we'll use the coefficients 1, negative 8, 21, and negative 20. We'll drop down the 1. 1 times 2 minus I is 2 minus I. Then I'll add negative 8 plus 2 minus I. That's equivalent to negative 6 minus I. Now we'll have to multiply 2 minus I times negative 6 minus I. Let's do the scratch work here. 2 minus I times negative 6 minus I. This will simplify as negative 12 minus 2I plus 6I plus I squared. Negative 12 and the negative 2I plus 6I gives me 4I, and I squared, that's equivalent to negative 1. This simplifies to negative 13 plus 4I. This now can be inserted into our synthetic division process. That's negative 13 plus 4I. Then we'll add 21 plus negative 13 plus 4I. That's going to give us 8 plus 4i. Then we'll have to multiply 2 minus I times 8 plus 4i. Again, we'll do the scratch work here on the left side. 2 minus I times 8 plus 4i. This is going to give us 16. 2 times 4i is 8i. Negative 8 times I is negative 8i. And negative I times 4i is negative 4i squared. We can simplify. The 8 i's cancel out with the negative 8i. Negative 4i squared is positive 4 because I squared is equal to negative 1. So this gives us a 20. This gives us 20. So when we multiply 2 minus I times 8 plus 4i, we get a 20, which means the remainder is equal to 0. The remainder is equal to 0. That's exactly what we expect because we're given that 2 minus I is a 0. So we should definitely get a 0 for the remainder. Now I can use synthetic division with 2 plus I. We can start with 2 plus I now, and we'll divide it into our factor here. We'll divide it into 1 minus 6 minus I plus 8 plus 4i. So let's use those as our coefficients. We have 1, negative 6 minus I, and then 8 plus 4i. And again, we expect that the remainder should be 0 because we know the conjugate is also a 0. We'll drop down the 1. 1 times 2 plus I, that's 2 plus I. Negative 6 minus I plus 2 plus I, that gives us a negative 4. 2 plus I times negative 4 is negative 8 minus 4i. And when we add this up, we do get a 0. That is exactly what we should get because we know the conjugate is also a 0. Now, what does this tell me? It tells me that this is a factor of our original polynomial. What this means is x minus 4 is a factor. It's a factor of our original polynomial f of x. Since x minus 4 is a factor, this implies that x equals 4 is a 0. So let's summarize. This implies that our zeros are 2 minus I. We got that from the problem. It's given that 2 minus I is a 0. And we know that the conjugate 2 plus I is also a 0. We use synthetic division twice to conclude that x minus 4 is a factor, and therefore 4 must be also a 0. So we have 3 zeros in this problem: 2 minus I, 2 plus I, and 4. Question 10. Let's list all possible rational zeros. Find all the rational zeros and then factor f of x. F of x equals x cubed minus 7x squared plus 7x plus 15. Let's use the rational root theorem. P is 15, and all of the factors of 15 are plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. Q is our leading coefficient, that's a 1. And all the factors of 1 are just plus or minus 1. So according to our rational root theorem, all of the possible factors of this polynomial are the ratio of P over Q. So we have plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. I'm taking the plus or minus 1 and dividing it by plus or minus 1. I'm taking the plus or minus 3 and dividing it by plus or minus 1, and so on. So these are all of the possible rational roots of our function. That completes the first part of the problem, looking for all of the possible rational zeros. Now the second part is actually to find the rational zeros. So I always start with the easiest number first. We'll start off with positive 1 and hope we get lucky. So let's use positive 1, and I'm going to use synthetic division. The coefficients are 1, negative 7, 7, and 15. If we get a remainder of 0, then we know that 1 is a 0. So let's start our synthetic division process. We'll bring down the 1. 1 times 1 is 1. Negative 7 plus 1 is negative 6. 1 times negative 6 is negative 6. This is a positive 1. 1 times 1 is 1. And I get a remainder of 16. The remainder is 16, which means 1 is not a 0. 1 is not a 0, so we have to continue on. Let's try negative 1. This is a trial and error method, but let's hope we get a remainder of 0. We'll drop down the 1. Negative 1 times 1 is negative 1. Negative 7 plus negative 1 is negative 8. Negative 1 times negative 8 is positive 8. 7 plus 8 is 15. Negative 1 times 15 is negative 15. And we do get a remainder of 0. That's great. The remainder is 0. We get that the remainder is 0. Therefore, negative 1 is a 0. Since negative 1 is a 0 of our original polynomial, this implies that x plus 1 is a factor. Since x plus 1 is a factor of our original polynomial, let's recall what that was. X cubed minus 7x squared plus 7x plus 15 was our original polynomial. And since x plus 1 is a factor, we can rewrite this as x plus 1 times our remaining factor. We already found that our remaining factor through synthetic division is x squared minus 8x plus 15. But wait, we can do more than that. We could factor this part using the diamond method. It factors as x plus 1 times x minus 5 times x minus 3. So our original polynomial can actually be factored as x plus 1 times x minus 5 times x minus 3. Since these are the factors of our original polynomial, we can find the zeros. The zeros are negative 1, positive 5, and positive 3. So this completes the problem. We can factor our polynomial as x plus 1 times x minus 5 times x minus 3, and this allows us to conclude that the zeros are negative 1, 5, and 3.